pH is 3 units below pKa, is this one. What does the meaning of that? Means that if you put your acid into a really lowest pH in here, lowest pH, and this solution already have a lot of hydrogen ions, yeah, so you can see we have a lot of hydrogen ion. So this your acid is not going to dissociate a lot, so only you can see just 3 of them, for example. That's an example. So just 3 of them, they just dissociate, and most of the molecules in this solution are whole molecule, so they are non-ionized. So that's the idea of non-ionization here in this graph. So what does the meaning of that? Means that just a couple of the acid molecule, they dissociate, but 99.90% of them, they don't dissociate. That's the idea. So for the second solution, that's the second solution. So this is the second solution. The pH is a little bit higher, so it means that we don't have a lot of hydrogen bond. So if you compare with the previous one, so we have less hydrogen ions. So again, we put this acid in this container, but so you can see that it dissociates more. So the dissociation of that is more, because there are a lot of space for hydrogen, giving hydrogen or ionization. So we will have less non-ionized. So you can see here, instead of 90.9, we have 99%. So it's a little bit lower than this one, for the first one. So for the last solution, we will put our acid into a lowest acidity, the lowest, this solution is less acidic. So what does it mean? It means that the pH is the highest one. Just a second. This should be 1 unit. 1 unit difference between the pKa and pH, and that's related to 1 unit. This is related 2 units, and this one is related to 3 units. 3 units. So for the last one, you put your acid in this solution, so it will dissociate a lot. So it will give a lot of hydrogen. So here we have the most ionization, most ionization, and the least whole molecule or non-ionization. So now you can see in the third one, you have 90% non-ionization. Yeah. So again, in this part, I just want to explain that what's the meaning of that. So if you have 3 units below pH, your pH is 3 units below. What does it mean? It means that your pKa is 3 units more than pH, or pH is 3 units less than pKa. So in this case, so if you calculate Anderson-Hasselbalch, you will see that how we get these number 3, -3. So that's your minus 3, 10 to the power of 3, because when you put something bigger in your pKa, so then you will put it back here, and then it would be -3 or -2 or -1. And what's the meaning of -3? Means that the concentration of this ratio, the ratio of the ionization and non-ionization is 1 into 1000. So that's why we have 10 to the power of -3. So that's for the first one. Now I'm just explaining the second one, 2 units. What's the meaning of 2 units below pKa? It means that pH is 1 unit below pKa. So if it's your pKa is this, and 2 units, your pH is 2 units less than that. So we are talking about 10 to the power of -2, and 1 in 10 is the ratio of ionized compared to unionized. So one of the acids is dissociates, and 100 of them, they don't dissociate. So this ratio is 1 in 100. So that's the dissociation. If you want to get the non-ionized one, it means 100 of them, or 90 of them don't dissociate. They are non-ionized, and 1 of them is ionized. So for the last one, when last one is 1 unit, pH is 1 unit below pKa. What does it mean? When you have 1 unit, your pH is 1 unit below pKa, so you will bring your pKa this side, and then you will get -1. So -1 means that 10 to the power of minus equal to the ratio of the ionized over non-ionized. So that's the idea of the ratio of ionized to non-ionized. But this graph is talking about non-ionized, so we are looking for non-ionized. So the ratio is 10 times bigger than non-ionized is 10 times bigger than ionized one. Yeah, non-ionized is 10 times non-ionized is more than ionized one. So we are looking for this table and this graph. Now we are talking about when the pKa and pH are equal. So if they are equal, so when you bring the pKa back, so they will cross each other, and then you will get 0. So the ratio of the ionized over non-ionized is 1. So 50 of the molecules of acid 1, we are looking for this line. So because we are talking about acids, so if we put this acid into the solution, that the pH of the solution is equal to pKa of this acid. So 50 of the molecules of AH will dissociate, 50 of them will dissociate or ionized, and 50 of them still they are not ionized. So you can see the 50% of that they are non-ionized. So now we gradually increase our pH. So the solution we are talking about, our solution is just going to be basic, because you can see that the pH will increases. So if the pH increases, if your pH increases, what does the meaning of that? It means that this value is high and this value is a little bit smaller in compared to our acid. So if I want to bring pKa behind the equation, so you will get positive number. So as you can see, so I'm just going back to this table. It's the same as this one, so just because it's near to my graph, so that's why I just written that again. So if log of A minus over AH or this equation equal to when we have 3 units above pKa, your pH is 3 units above pKa, like this. So the ratio of ionization would be 1000 to 1. And what is the 1? It's non-ionized molecule. So most of your molecules of your acids, they dissociate, but as you can see that we are looking for non-ionization. So 0.1 of percentage of these molecules they are not ionized, so that's why we have this point in here. In the case of 2 units pH above pKa, so 2 units of pH is more than pKa, so you will get 2. What does it mean? It means that you have 10 to the ratio of the ionized over non-ionized is 10 to the power 2. That's equal to this one. So now 99% of this your acid they dissociate. So 1% of them they don't dissociate, so they are not ionized. And also, if the your pH is 1 unit more than your pKa, so when you bring it back to the equation, you will get 1. What does it mean? It means that you have 10 to the power of 1. It's the ratio of the ionized over non-ionized one. So that's related to 1 pH above pKa, and 9% of the acids that you pour into your solution, 90% of them they don't dissociate, or they are non-ionized, and 91% of them you get the ionized one. For this graph, so the blue one is for base. So imagine that you have a container that it has a lot of hydrogen ions in there. What does it mean? It means that your pH is really low, so it's so acidic. So then you will pour some basic molecule or basic drugs into this container. So this base molecule loves to gives a lot of hydroxide ion. So if you, for example, if in this container you have 5 hydrogen ion, so this base will give 5 hydroxide to just neutralize the hydrogen ions. So at the end, so this base gives 5 OH, so it means that 5 of its molecules they dissociate. But if you put this base into in a container or in a solution that it has less acidity, it means that we have less hydrogen ion. So we don't need to give a lot of hydroxide ion to neutralizing all of them, because we have just 3 hydrogen ions. So that's this base just dissociates 3 of these molecules, they dissociate to just neutralize the hydrogen. So the ionization is less. And so most of the molecules, they would be whole molecule, they are not ionized. As you can see, it's gradually when we increase our pH or make it more basic or less acidic, so our base doesn't need to just dissociate to produce hydroxide. So when you reach to the difference between pKa and pH, the difference between pH and pKa, so you can see that you have more whole molecule in here, because we didn't give any kind of or less kind of hydroxide ion.